Hall effect sensors. Description, operation, difference with the Hall effect. This is our second ignition input that we're going to be talking about. What's different with the Hall effect is it's 3 or 4 wires as opposed to the VRS that's 2. The VRS makes its own voltage, as the Hall effect needs an external power and ground to function. Okay? The Hall effect also is going to produce a digital signal. The output is digital. It is a square wave as opposed to a VRS that's an AC sine wave. So amplitude is constant. A VRS signal, you're going to start weak and it gets bigger and bigger. Amplitude increases, frequency increases, where a Hall effect is going to be a square wave of variable frequency, but the amplitude stays the same. So in theory, a Hall effect is a better low-speed triggering device than a VRS is, because the amplitude is consistent. It doesn't change. And as I mentioned earlier, we have to be careful in identification with number of wires, because some of the new Hall effect some of the new wheel speed sensors they're using on ABS systems are Hall effects. It's a 2-wire. It still has a power. It still has a ground. The ground's on the housing, and the signal is digital. So it's a 2-wire Hall effect. So we have to be careful in making absolutes when we say number of wires. And again, when we're counting wires, we're not talking about other sensors. You know, we're not going to look at, say, a coolant temp sensor and say, well, that has 2 wires, so that's a VRS. No, we're talking about revolution sensors here. Something that's measuring the rotation speed of something. If it's got 2 wires in general, it's a VRS, AC sine wave. If it's got 3 wires in general, it's a Hall effect. So very, very briefly, with these Hall effects, we've talked about this before in section 2 when we talked about switch inputs. So there's going to be some repetition here as far as circuit design, pull up, pull down circuitry. But the heart and soul of a Hall effect, truthfully, is a transistor that's inside of it. And so what you have is, this would be one type. You'd have a permanent magnet, and then you'd have a Hall element. And inside of this Hall element is a transistor. Now there's other components inside of this. In fact, this was named after someone. This is their last name, who discovered this device and how it operates. But to put this simply, what you're going to have is this magnet. When it's exposed to this Hall element, it's going to switch the transistor on. And what they'll do in some designs is they'll run blades that are going to fall in between this. And when a blade is in between there, what that's going to do is shield the magnet, and that's going to turn the transistor off. When there is no blade in between, the magnet's going to contact this Hall element, and it's going to switch the transistor on. That's as simple as I can put it. There's some other internal circuitry inside of this device that I'm not talking about. And truthfully, it doesn't matter. And the reason it doesn't matter is we're not building them, right? We just need to diagnose them when they're bad. So the main component we want to think about with the Hall effect is a transistor, and it's going to switch on and off. When it switches on and off, it's going to switch a voltage either high or low, digital, on off, just like our other switch inputs. So our signal is either going to be pull up or pull down design. Now if I can draw this and simplify it for a second, if I have a computer and I have a signal wire for my Hall effect, we can draw for now, we'll draw the Hall effect as a switch. What is a transistor? It's an electronic switch. So in my generic picture here, this switch would be my transistor. If I were to draw this picture with this going to a positive source, what type of switch input would you call that? Pull up or pull down? It's a pull-up design. With the switch open, we're going to have 0 volts on this line. With the switch closed, we're going to have source voltage anywhere between 5 and 12. We'll call it 12. When the switch opens again, this drops to 0. Switch closes, this goes to 12. So it's going to be a digital square wave on the signal wire. And what's going to change the signal and make the signal look a certain way would be the switch itself. In fact, take it even further, that signal is going to look identical to whatever the reluctor or drive plate looks like, the way it's cut. How many windows is going to be exactly how many square waves you have per rotation. So that'd be a pull-up design. I drew this way. Again, just trying to simplify this. Draw the Hall effect transistor as a switch and then run this to ground. What type of design is this? It's a pull-down design. So internal to the computer, you would have a resistor and a source. And as long as the switch is open, let's say it's 12, we're going to have 12 volts here. We'll have 12 volts all the way out here. Just close the switch. This drops to 0. This drops to 0. And you're going to have a 0 12 volt square wave that the switch is going to control again. So as I stated, the Hall effect is an electronic switch, okay? And if we're dealing with switches, we're dealing with switch inputs. That section 2 would be a good review if you're unsure of what I'm talking about with pull-up and pull-down design circuitry. Go to section 2 and review all of the information that we talked about with pull-up and pull-down. I have some generic pictures of circuit design. We'll go to this one first. And this is a pull-down Hall effect picture, page 27. And what we're looking at is we have a power, we have a ground. We need both of those for this thing to function. There's an integrated circuit inside of there. I've just drew it as an IC. It contains an amplifier, an AD converter, and some other stuff. We need a power and ground for this thing to work. But that's all involved with the base circuit of the transistor. So all that stuff's involved with the base. We don't worry about that because we don't go inside of this and do anything. We just make sure we have power, we make sure we have a ground. I drew this one as a pull-down design. Let's say our source is 12. So we have 12 volts going across the resistor. As long as this is off, we'll have 12 volts that extends all the way out to the sensor and this transistor. As long as the base is off, there is no ground for this circuit. If there's no ground, what's the computer going to see at this voltage sensing circuit? It's going to see 12 volts. We'll have a high voltage on that line. As soon as the base is switched on, which is going to have to do with the magnet that's coming in contact with this device, the magnet's going to be the catalyst, if you want to call it, to switch this transistor on. As soon as the transistor is turned on, the base circuit's turned on, it allows this signal. In this design, you can see that we're going to take this straight to ground, and that's going to pull this signal low. We have this resistor inside that's creating the voltage drop. This is going to end up being 0 volts at the computer, and we're going to have a 0 to 12 volt. In our case, I use 12 as an example. 0 to 12 volt square wave based on the amount of switching of this transistor. That is our pull-down design. Our pull-up design, this is page 28, and I drew it this way. I'm not sure how accurate this is, but this just gives you an idea of design. Notice the voltage sensing circuit in the computer. We don't have a resistor in here. It's just watching now, right? We're looking for a voltage coming in, not watching what we're sending out. Still need my power and ground for this to function. Let's call this 12 volts coming in. So we have a 12 volt feed. Does what it needs to for this IC, the integrated circuit. That would be the AD converter and amplifier that's in there. It's also going to extend and go across the resistor inside. as long as this transistor, actually, let's skip the resistor for a second. Oh, we don't have to. As long as the base is turned off, what's the voltage going to be right here? It's going to be 12. Even though we have a resistor here, it's going to be 12 here, it'll be 12 here, no current flow, no voltage drop. Okay? As soon as this transistor is turned on, we're going to extend this 12 volts all the way to this voltage sensing circuit. Now that voltage sensing circuit does not support current flow. So again, even though we have a resistor here, we're still going to have 12 volts at the computer. How do I know there's a resistor in here? Why did I draw it with the resistor? Why did I just draw it as a straight line? Because on this design, if the signal wire shorts to ground, if there was no resistor internal, that would take out the power feed to this Hall effect. And that's not what happens. I've seen these signal wires short to ground. As soon as you fix the short, it comes back to life. You never lose the power feed. So truthfully, on this design, the only reason the resistor is there is to protect this circuit from a short to ground. That's it. It's a pull-up design. To simplify it, what are we doing? If you look at this picture, it is very, very similar to what a pull-up switch input design looks like when we drew it in section 2 as a switch going to positive. With the switch open, you read 0 volts here. With the switch closed, you read 12 volts here. Pull-up design Hall effect. So when you're testing these, it's important to know circuit design. You need to know your circuit design when it comes to detailed tests. In both cases, you're going to have to check your power, check your ground. Unlike the VRS input that makes its own voltage, this one you need to check for an external power and an external ground. As far as the power feed goes, it can be anywhere from 5 to 12 volts. Is your typical Hall effect design, power feed. In fact, most of the cars today are using 5 volts to power them up. But there are still some 12 volt ones. Our ground, we want our ground to be less than 100 millivolts. Okay. And then the signal, we'll kind of bypass this. The signal is going to be unique to the system you're working on. If you're working on, say, I'll show you a picture of one. If you're working on a system like this, you see the harmonic balancer has 3 blades. So what are you going to have? Per 360 degrees of crank rotation, you're going to have 3 unique square waves. It's going to be unique to the application. Or if you were looking at one like this is a dual Hall effect. This is on a GM 3800 that you have 18 windows on the inside and 3 windows on the outside. You're going to have a signal that looks like this. You have an 18x and 3x crank signal. Yes, sir.
Now, why is it broken up into 2 signals?
Why is it? I was afraid you were going to ask me that. Every system's different, and I don't want to get lost in this part, but this is all about identifying coils and which one to fire. Okay, so let me take you to this one. And I used to include this as part of the class. It's really not necessary because, truthfully, it's only 2 different designs. The old school GM 3.8, when it first came out, the sequential fuel injected 3.8, that was the crank sensor on. And the design on this car was it had a module, the ICM, and that ICM controlled the 3 different coils. Okay? And so what all these extra signals are about is telling this module which coil to fire first. And on this design, what you have is just simply a 3x signal, and that's it. There's nothing else. So if you spin the crank 360, what do you end up with? You got 1, 2, 3 different square waves So say this is 360 degrees right here. And then the next 360, so 1, 2, 3 again, you have another 3 square waves. Is there any identification signal in the crank sensor that tells the module which one's which? Or are they all even and uniform? They're all even and uniform. So this module has no idea which cylinder is which. Okay? On this design, the cam signals needed to synchronize these. So in this old school design, the cam signal would come into play and it would identify a cylinder that is, or a pair that's about to fire. Okay? Cam sensor signal was necessary for spark control on this design. You needed both. This kind of emphasizes more section 22 when we do no start, no spark diagnosis. In the very beginning of that section, what I mentioned is some cars need both cam and crank signals for spark to take place, and some do not. This car, during cranking, needs both signals. Otherwise, the computer doesn't know what to do with it. Now, they called this a slow start because if the engine would shut off right here, it takes up to 720 degrees of crank rotation before you get another cam pulse, before the computer knows where to start sequencing these. So it's called a slow start system. When they updated it, they went to something that was called a fast start system. And that fast start system, it's the same engine, but they used a dual crank sensor signal now. And on this design, again, this is your signals. There's your 18X, there's your 3X. On this design, what it would do, this is what the module's looking at. Within the 3X window, there's one transition. Within the 20-degree 3X window, there's 2 transitions of the 18X. Within the 30-degree, there are 3 transitions. And what this module was able to determine with this is within 120 degrees of crank rotation, we can figure out where we are as far as which coil needs to be fired first. And that's what this very elaborate crank signal did. So I guess the short answer, Luke, would be every car is different as far as what they're doing. And it would really be pointless right now in what we're trying to do, which is simply to check the Hall effect. Right now, it's kind of pointless to go through all the different designs and explain how they're working, because every car is different. And you're going to have to research that. I mean, we could literally do 10 different designs, and that is only just scratching the surface of them. And truthfully, guys, we're not making the car. We're not making the system. So that part really isn't that important as long as you're able to understand how to check the signal and say, that's good, that's not good, let's move down the list. When this becomes important is when you have certain symptoms, and to know what you need to check and what you don't need to check. You know, for example, on this car, I don't need a cam sensor for this car to run, because the computer is able to figure out which module or which coil is what, and the cam signal comes into place for sequential injection. If it never receives a cam signal, it just fires them in a group fire design, or it fires them in random and your firing's off a little bit with the injectors. But on this design, if I lose my cam signal, the car is a no start. So you see where maybe that becomes important at some point in time. What do you need to check? What do you not need to check is important. I think for now, I just want you guys focused on the Hall effect itself. And this picture kind of emphasizes that dual crank sensor, the dual Hall effect. You can see that we have 2 different Hall effects. We have 2 different signals. They share a magnet. The other thing that they're going to share is they share a ground, and then they're going to share a power feed too. So your 4 wires coming off of that would be 1, 2, shared power and ground, an 18X signal, and the 3X signal. That would be your 4-wire Hall effect. Yes, sir. The question is if you're missing one of the 2 signals, cam or crank, is the car going to start? Is it not going to start? The answer is it depends on the design. Some cars don't need the cam sensor to start. You'll still have spark. It'll still start without the cam signal. Some cars need to have the cam signal to start. And so I just gave you an example of 2. that you know, that's just the same motor in different years. But we're going to talk more about that in section 22, and I'll elaborate on that a little bit more. It's the Hall effect we want to focus on right now. All right. So check the signals. If it's got two, the one we just went over, two signals on a 4-wire, we're going to want to check it cranking or running. Why cranking? Maybe the car doesn't start. If you're doing it running, of course, you're looking for maybe cam-crank relationship or something like that. But in most cases, you're going to be doing a cranking test because the car doesn't run. So if you don't have a signal, check your power, check your ground, and then you're not done. If you have no signal still with a good power and ground, then we need to make sure that our signal wire isn't opened or shorted, or we have a bad module, or some type of mechanical failure before we replace the Hall effect. And what we're going to do is some bypass testing. We're going to follow this with some pull-up, pull-down flow charts, and of course, right here in capital letters and a bunch of exclamation points, you have to know if the circuit is pull up or pull down to properly diagnose these. I have included, and I'm not going to go over this, I've included some pull down testing procedures. It's kind of a trouble tree. So this is similar to what we've done previously. Section 2 is just written in a different way. Signal voltage measured at the switch is fixed low. What do you do? Signal voltage measured at the switch is fixed high. What do you do? I have some videos we definitely want to watch here that apply to this. I think now will probably be as good a time as any. So these 3 videos we want to watch, and then some pull-up testing, same thing. Signal voltage measured at the switch is fixed low. Signal voltage is fixed high. And then the unique part with the pull-up is you can have a trouble code with a functional switch. So we need to talk about that one too. These are going to be a nice review. Page 26 will be a nice review after watching these videos. So I think at this point what we're going to do is we're going to watch those, and then we'll come back to this and we'll talk about it.